quantum computing at NVIDIA. And today I'm going to talk about our perspective and approach to quantum computing, specifically how to start thinking about using classical computers both to research quantum algorithms ahead of time, and near and long term, how to program quantum and classical systems together, which is what we believe is going to be needed for quantum advantage. So just for a brief bit of perspective on quantum computing, I don't know the range of expertise in the room, but I guess the important thing to understand about quantum computing is it's a fundamentally new model of computing. It's not just the newest accelerator or a new type of parallel computing. It's based on fundamentally different physics, and that leads to some limitations, but it also leads to tremendous opportunity. And so there are already algorithms where we expect an exponential or quadratic speed up from using quantum computers, and we expect that more will be discovered, and there will be applications long term that are hard to predict today, just because of the new physical power being leveraged. In terms of progress today, this sort of panel in the middle is a chart of scale of quantum systems versus time. There's been tremendous progress in the last decade. We've gone from systems with 1 or 2 qubits, mostly academic research only, to now systems with tens or hundreds of qubits, now being made available to users over the cloud as a service. So very exciting to see that with the tremendous investment. We expect that to continue, but it's also important to understand that we're a ways away from the time where we expect to see a quantum advantage on useful problems and quantum advantage in production. So this is not only a question of scale, it's a question of fidelity. So because quantum systems are inherently error prone, and because the error accumulates through a calculation, you need very high fidelity, likely perfect qubits achieved by quantum error correction in order to run most problems. So there's scale that needs to increase. We need more physical qubits to represent logical qubits. There's fidelity that needs to increase. We need to get error rates down to be able to run quantum error correction, and maybe to see an advantage in the near term before that. And then there's speed that needs to increase. So quantum gates are slow compared to classical gates, especially if you're doing error correction. And to see an advantage in practice, even if there's an algorithmic one, we have to get that time down. So in addition to improving quantum hardware, what do we need to do in the meantime, and what can we do that can help? One big thing is algorithms research and linking algorithms to applications. So this has also been an area of tremendous progress in the past couple decades. We have researched all kinds of new algorithms for applications like quantum chemistry, for optimization problems, for quantum machine learning, and we see this as potentially like bringing the timeline closer, but bringing possible quantum advantage closer. So algorithms and applications research in order to understand what you can do with a quantum computer, what you can best do with a quantum computer, and when you can do it, and what the requirements are, is very important. And then the other big area is how do quantum computers fit into a broader accelerated computing framework? So because of the inherent limitations of quantum computers, there will be some things that they're never good at. So no matter how good the quantum computer gets, you may never want to use it for dense linear algebra, for example. And the model that most people are going towards is hybrid or integrated quantum classical computing. So a quantum computer closely coupled to CPUs and GPUs, each one kind of handling the tasks that it does best. And so figuring out how to do that from a physical hardware perspective and from a software perspective is really important, in a way to kind of get a jump start towards useful quantum computing. So here at NVIDIA, we build GPUs, we build supercomputers out of GPUs and CPUs and networking technology. And so we're thinking very hard about what we can do to enable these important kind of threads in quantum computing and quantum computing development. And so the first area is quantum simulation. And so this is targeting quantum algorithms research. So because quantum computers today are so limited in terms of what can actually be run on them, if you're trying to do algorithms research at the cutting edge, or understand what tweaks to a quantum algorithm might make it better for a particular application, or understand the requirements for a quantum advantage for a particular problem in terms of scale or error rates, simulators are the best tool for that. And simulating quantum computers is a great use case for GPUs. So I'll talk a little bit about that sort of at the first part of this talk. And then the other big area we're working on is hybrid quantum classical computing. So this is, as I mentioned, tackling the problem of how do we make quantum computers a useful part of an integrated computing system? How do we give a programmer who's not necessarily a quantum engineer or an expert in quantum computing, but maybe has a quantum chemistry app they want to bring? How do we make it easy for them to leverage quantum computers, to understand if and when they might see an advantage from quantum computers? And how do we build a software framework where you can actually get the best performance possible, eliminate other bottlenecks, so you can understand and do meaningful comparisons between classical computing, simulated quantum computing, and real quantum computing. So we're working very hard on that as well. And so I'll briefly talk about quantum circuit simulation. Most of this talk is going to be about QODA and hybrid quantum classical computing, but this is kind of the backbone underneath a lot of that work. So we develop an SDK called cuQuantum here at NVIDIA for accelerating quantum circuit simulations. It consists of two libraries, one for state vector simulation, one for tensor network simulation. And it integrates kind of invisibly as a backend into the leading frameworks that folks are using today. So most people are writing their quantum circuits in Cirq or Qiskit or PennyLane, or maybe using Amazon Bracket. cuQuantum's integrated into all of them. And what that means for the developer is you can get GPU accelerated performance without having to change any of your code. We also make a container available called the DGX cuQuantum Appliance. This is on our platform called NGC. Also can be deployed on any major cloud. And this is a kind of ready to deploy solution, which is cuQuantum accelerating Google's Cirq framework. And I'm showing this to kind of give you an idea of the performance difference you can expect, and to illustrate the point of how good GPUs are for quantum circuit simulation. These benchmarks on the right here, we're comparing a few different quantum circuits running with Cirq on a data center class CPU compared to 1 to 8 A100 GPUs. Even with one GPU, there's a nice speed up. As we get up to 8 GPUs, we see nice strong scaling up to a 70 to 300x speed up. So meaningfully different in terms of the kinds of circuits you can simulate and how fast you can do work. And then we announced last month that we're scaling this to multi-node. So one of the most important things we see, especially happening at supercomputing centers, is trying to run very large scale quantum circuit simulations to understand where the boundary actually is for quantum advantage, and to study scaling behavior of particular algorithms to understand, say if a tweak to a hybrid algorithm or a quantum machine learning algorithm might make it better suited for quantum computing. So we announced that we'll be releasing this later this quarter. We've run some benchmarks already with really nice results, about a 3.5x speed up over the what we understand to be the best state of the art for large scale quantum circuit simulation, and also added support for the Qiskit framework. So Cirq and Qiskit, which are the two most popular frameworks, are now both natively supported in the container, as well as having this multi-node support. And our goal, especially with cuQuantum, is to really enable the whole ecosystem. And we've had some nice success with that so far. So everyone from industrial research groups who are mostly trying to understand for a problem in pharmaceuticals or energy or finance, is quantum computing useful, and when will it be useful? That's a great use case for a simulation, to supercomputing centers, as I talked about previously, to quantum hardware and software startups who are maybe either doing algorithms research or doing things that might inform the design of their future processors, have all found a use case for a simulation. And so cuQuantum has been out for about 8 months now, and it's been nice to see that it's been useful for such a wide variety of groups. Okay, so that was kind of a whirlwind introduction to cuQuantum. I'm now going to switch gears and talk about QODA, but maybe I should stop and see if there are any questions.
I don't see any hand up.
I heard something very, very faint. Okay, well, maybe we can do it at the end, and I'll just keep going.
Yes, I can't see any questions in the chat yet, and
okay.
I don't seem to be able to see if there are any hands up with the audience. So, I
Okay,
guess just
yeah, that's fine. I can't see it either, so maybe at the end is best. All right, so that was cuQuantum, platform for simulating quantum circuits with performance and scale beyond what you can do with other simulators or quantum processors. Now we're going to talk about QODA, which is our platform for hybrid quantum computing. So the motivation with QODA, as I mentioned at the beginning of the talk, is that all valuable quantum applications are going to be hybrid. Kind of no matter the application, there are plenty of things that quantum computers won't do well, and you'll want to use classical processing for, and also a lot of kind of pre and post processing steps that you'll want to do on a classical computer. So whether that's circuit optimization ahead of time, or the classical side of a hybrid algorithm, or post processing for decoding errors for fault tolerant quantum computing, it's going to be very important to have tightly coupled classical computing resources. And if we kind of look at what's out there today, there's a lot of effort going into hybrid computing, which is great, but we see kind of some gaps that still exist, and one of them is performance. So most of the quantum computing frameworks that are very popular have been developed early on, intended for kind of low barrier to entry for quantum computing, and being able to run small problems easily, and that's great, and that's very important. But they're not built for performance, and they're not built for interoperability. And so if you're, I'll go back to the quantum chemist use case. If you're a quantum chemist and you have some code today that runs on CPUs and GPUs, and you're wondering, can quantum computing be useful for me? What you'd like to do is take your code and define parts of it that you want to port to a simulated quantum computer, or eventually a real quantum computer, and do comparisons. And that's not so easy now. You have to go learn a whole new language, figure out how to program that code in that language, and then do something to link it back. And it's likely that you'll have performance bottlenecks that will make it hard to do a real analysis of whether quantum computing is useful or will be useful. And so what we'd really like is to have a framework where you can program quantum computers on the same level as CPUs and GPUs and have a compiler that can compile to either the right quantum resource, the right simulated quantum resource, or the right classical resource. So from the programmer's perspective, you won't have to be as much of an expert in quantum computing, and you can kind of easily develop new hybrid code and get good enough performance to understand the value of quantum computing. And then once quantum computers are ready to actually be useful for applications, you'll hopefully have the code already written, have a good understanding of the value trade-off, and just be able to port it over. So with that in mind, we're happy to introduce QODA. QODA stands for Quantum Optimized Device Architecture, and the kind of echo of CUDA here is a bit intentional, because we see programming quantum computers now to be a bit like programming GPUs before CUDA, in that it was possible, and if you were very talented, you could get useful performance from it, but it was unnecessarily complicated. And so by kind of bringing GPUs up to the level where they could just be programmed in standard languages alongside CPUs, CUDA enabled a whole wealth of scientific discovery, and we hope to do that with QODA. So what QODA is, it's a single source extension of C++ and Python with quantum kernels, and the quantum kernels are then compiled by a compiler we developed called NVQ++ to a quantum intermediate representation, where they can be executed either by a simulated quantum computer, where maybe we can use cuQuantum on a GPU maybe, or a real quantum computer, where we're partnering to enable that, and I'll talk about that a little bit later. QODA is interoperable with the best tools for high performance classical computing. So that's CUDA and the CUDA enabled libraries, standard parallelism, OpenACC, OpenMP, and it's also open. So we will publish a specification, and we will open source it when we release an open beta. And in terms of partnerships, just like with cuQuantum, we intend to kind of enable the whole ecosystem with QODA. We are pre-release now, and so we're starting early with prioritizing different types of quantum hardware. And so you may know that there are a lot of different architectures proposed for physical quantum computers. It's not so clear yet what's going to be the best, or maybe a few will be good, maybe for different types of problems. And our goal with QODA is to make it easy for the developer or the researcher to leverage any type. So these 6 companies at the top are companies who are building different types of quantum processors: superconducting, trapped ion, photonic, neutral atom, and NV center. And so we're working with them early on to make sure that all of those types are kind of first-class citizens in QODA. Yeah, the developer has the ability to easily program any of them. We're also working with a few companies who are developing quantum software, who are thinking about how to best leverage quantum and classical resources together, and building applications on top of QODA to do that. And working with some supercomputing centers who are, either already or thinking about the integration of quantum and classical computing. And again, this list is by no means limited. We intend to, enable everybody with QODA, but this is the starting point. And just to quickly give you an idea of what QODA looks like, this is the variational quantum eigensolver written in QODA C++. So at the top here, we're defining the ansatz, and so that's with a QODA quantum kernel. Then the Hamiltonian is defined in the middle with this QODA spin-out function via Pauli tensor products. We define a classical optimizer in QODA, and then run the variational quantum eigensolver with a one-line call. So very simple piece of code. Wanted to start with something that's kind of familiar to most people who are looking at quantum algorithms with it, which is VQE, and show you that in QODA this kind of is simple and looks like C++, and the Python APIs look like Python. As I mentioned, it's interoperable with the best tools for supercomputing and GPU supercomputing, and I'll show an example of that on the next slide. So this is an algorithm called quantum imaginary time evolution, like VQE. It's a hybrid algorithm. It consists of 2 steps done iteratively. First, computing an expectation value. So this is something that you may want to do on a quantum processor, done here again with the QODA spin-out function. And then the classical step is some dense linear algebra. And this is likely something that you'll never want to do on a quantum processor, but it's a great fit for a GPU. And there's tons of work already gone into software to optimize for that. And so here you can, in one line, leverage QSolver for it. And so again, this is a very simple code snippet, but already this is something that would be pretty hard to do in other frameworks. And so kind of shows how by elevating quantum circuits to a higher level, it's much easier to be interoperable with high performance classical processing software. We're early days in benchmarking, but I mentioned that we expected a performance advantage, and so far the results of that are promising. So this is again a variational quantum eigensolver, a single iteration where we're comparing code written in QODA compiled with NVQ++, simulated on an A100 GPU, compared to code written and compiled in a leading Pythonic framework, also simulated on an A100 GPU. So this is not a GPU to CPU speedup. The hardware here is identical. This is a pure software speedup. And the numbers are kind of small. I apologize for that, but already at 20 qubits, we're seeing about a 287x speedup, obviously with a really nice trend as systems scale. So again, we're early stages in benchmarking, but early results are promising as far as in addition to the ease of use and interoperability, there being a big performance difference using QODA as well. And the last example I want to show is, in addition to advantages on things that you may have already been doing, QODA will enable, we hope, some novel quantum research. So, one thing that people have been looking at and thinking about is parallelizing a workload over many quantum processors in order to hopefully get an advantage before a big quantum processor is ready. So this is something that is going to take a while to be able to execute physically, and then take even longer to execute physically with meaningful results. But already you can simulate it in QODA. So this is code to run VQE, except where we're assigning each A100 in a DGX A100 to be a virtual QPU, so a simulated quantum processor. And then we're factoring the Hamiltonian and simulating it in parallel. And we see really nice strong scaling over our simulated QPUs. And so again, hopefully a pretty small and simple example that illustrates that this will kind of make novel kinds of research into quantum computing and hybrid quantum classical computing possible. So you can imagine, pretty easily simulating different types of quantum processors for different problems or different parts of a problem, and all kinds of novel configurations. So we hope QODA will make that much easier. And so, yeah, I mean, I'll just wrap up. I presented two platforms today, cuQuantum and the DGX cuQuantum Appliance, which allows you to simulate quantum circuits with high performance and push the scale of what you can do for quantum algorithms research, and then QODA, which kind of steps back and looks at the application perspective and how we can integrate quantum computing with classical computing and get the best head start on that now. And there's obviously a really nice synergy between the two, and we hope that this is, both tools are broadly useful for the quantum computing community. So that's all. So thank you for your attention. I'll take questions if there are any.
So, can you see the Q&A?
Yes, let me. Yeah, will QODA be available in Fortran, like CUDA Fortran? That's a great question. We're going to start with C++ and Python, but Fortran is in the plan. It's just going to be after those languages, and it's one thing we're doing now is getting feedback on priorities of languages. So knowing that Fortran is important to users is really good.
I have a question. Is there any plan to standardize this approach to, let's say, to the C++?
Yeah, so for the near term, I think what I can say is we're going to try to follow the standards work that's already going on in C++ and other standards committees. We think that it's a little bit early to talk about standardization for quantum computing. There's just so many unknowns. So I don't know if I can say something concrete about plans for that. I think the plan now is to try to enable the research community and listen to what people are doing and what people need and take it in that direction.
I guess I have a question, Sam, which I probably should know the answer to, but I don't think I do. Just in terms of you're talking there about using the DGX A100, obviously, which is a very particular type of system that we provide. What do we have any sort of idea of what sort of performance we see on a more generic GPU-based system, which perhaps doesn't have the NVLink, the fast interconnect between the GPUs, and is maybe the PCIe version rather than and so on? Yeah.
Yeah, that's a great question. I don't have charts to show, unfortunately, but and the answer is complicated also, and it really depends on the problem. So for large-scale quantum circuit simulation, there will be a difference just because you often get limited by internode communication bandwidth. But one thing we do with cuQuantum and the cuQuantum appliance in particular is in our container, we under the hood, do some things around smartly swapping bits in the state vector to minimize the number of gates you need to do across nodes, and also scheduling things. So while those communications transfers are going on, to run other gates. So there is a difference, but we do see a big gap in performance either way using cuQuantum versus not.
Thank you. So a question to Viv, actually. So given you have a much better understanding about what you and your research teams are doing in this area, do you see that something like QODA, I'm not sure, I would never quite sure how to pronounce it, would be of use to you and your research community and what they're doing?
I expect so. For us, it depends on which HPC systems that the community generally has access to are able to implement this. And if they're NVIDIA supplied, quite likely you guys will be talking about adding this to the suite of available stuff. So there are other, it's kind of also a little bit what level, because there are several codes that people are using to simulate quantum architectures in the UK that can probably take advantage of GPUs, but how they'd integrate with this, I'm not sure at this stage. That we'd have to talk more to the developers. But in principle, yes, and it'll be availability, ability to just play with it because it's installed on the kit we're using. That will make the difference.
Yeah, so the container that Sam mentioned is probably a really good place to start, certainly for the QQuantum stuff, because it's just a Docker container, so you should be able to deploy that on any GPU system.
Yeah, maybe to build on that, the nice thing is there are a few different entry points. So if you're a developer who's developing your own simulator framework for quantum circuits, then you can just take the cuQuantum SDK, and that's quite low level and flexible. It's meant to be kind of integrated into different frameworks and already has been with the leading ones. And we're happy to support integration into other frameworks. And then if you're at the level of a researcher looking at quantum circuits, and you don't necessarily want to work on framework integration, you can just take the container as Paul mentioned, and that's kind of out of the box, great performance. And then with QODA, QODA kind of sits above quantum simulators, and so I think the use case there is, if you're either coming from a quantum first background or an HPC first background, and curious about the integration of the two, and you want to develop some new hybrid code, say a quantum generative adversarial network where the generator is classical and the discriminator is quantum, or something like that, then QODA will kind of allow you to use different quantum resources, be those simulators or real, as well as classical resources.
So one thing is when you simulate quantum circuits in general, the memory needed increases kind of exponentially with the number of qubits that you need to simulate. How does this go into NVIDIA? Because in general, the GPUs tend to be kind of restricted. So how well is to distribute the qubits over memory and things like that?
Yeah, that's a great question. So for kind of pure state vector simulation, that's certainly true. You get limited by how much memory is available, and so that means that even on a supercomputer, it's somewhere in the 40s or maybe up to 50 qubits. And so if you're doing that, the benefit of cuQuantum is to run circuits at that scale much faster. So you may know that for lots of algorithms at that scale, it gets to be prohibitively slow to run classically. So it's a speed up rather than a scale up. Where it does enable a scale up is, I guess in a couple ways. So first is methods like tensor networks. So tensor networks, too long to go into here, but the idea is that if you you don't need the full state vector at the end, and what you need is some expectation value or a reduced density matrix or something, the state vector method is overkill, and by modeling the circuit as a tensor network and simulating by contracting the tensors, you can scale much higher. So I didn't show it in this talk, but we have a couple examples now of people simulating circuits with thousands of qubits, and that's going to be limited in terms of the depth you can simulate and the types of algorithms you can simulate. So it requires not too much entanglement, but that's a way to scale up. And then there are even with state vector simulation, there are methods to get around the hard memory scaling. So we actually partnered with Xanadu this summer. So they took cuQuantum, ran it on the Perlmutter supercomputer, and came up with a novel technique to kind of it's called circuit cutting, and we're able to simulate accurately simulate a 129 qubit circuit using a bunch of different 30 qubit circuits. So there's no free lunch, of course, but there are options, and the cuQuantum is flexible enough and QODA is flexible enough that it hopefully makes those options a lot easier.
Viv, I see you have your hand up.
Yes, so one question, so you've shown benchmarking with VQE, and VQE is the easy one to do, right? Because the quantum does its quantum thing and the classical tweaks the controls, right? Have you benchmarked or even looked at doing anything else where the data has to pass between classical and quantum? And if so, do you have any results you can share on that yet?
Yeah, that's a great question. Unfortunately, no. So I don't know if I said this in the talk, but we're fairly early on in QODA. We're going to the plan is to have an open beta in March of next year, and so we're a bit limited in benchmarking we've done. What I will say is for things more complex than VQE, no promises, but naively I'd expect it to be even better, because VQE doesn't really need a lot of intensive classical resources. But if you imagine something where you need to encode something as quantum data, and that encoding is computationally complex, so this comes up in drug discovery, then QODA might be quite a lot better than frameworks that make it hard to use high performance classical resources, or again with quantum machine learning type algorithms where the classical processing is non-trivial. That's where I think I would expect the most advantage from QODA. Unfortunately, I can't quantify that yet.
Yeah. Second question is does it only do gate model, or will it interface with quantum annealing or other architectures? Because there's more even than that you might want to interface with in terms of what the quantum processor naturally does.
Yeah, so we're already partnering with some hardware vendors who are doing not quite gate models. So neutral atoms, there's the more like analog Hamiltonian simulation use case, and even photonics, it's kind of more like continuous variable quantum computing. So those will be supported. For annealing, the intention is to support it also. It's what's not clear yet is if there's actually compiling that needs to be done, or if it's just a case of making it interoperable. So if it's just making it interoperable, that's quite easy. But we're thinking about if there's any compiling steps or optimization steps that could be helpful in QODA.
Mm-hmm. Cool.
So I'll stop the recording.